Okay, this is our final information that we need about power series. And there were three different power series or Maclaurin series or Taylor series or Taylor polynomials, all of those things that you needed to have memorized. And that was for e to the x, sine of x, and cosine of x. And we'll write those all down here to remind us of what those are. And then there's one more that you need to have memorized, and these are all required things. So e to the x, remember, was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus and so on, and you could just write it as x to the n over n factorial and so on. So this was the series. So we have an equal sign. If we do the polynomial, remember we just put the squiggles, not equal, and then we wouldn't have dot, dot, dot on the end because it would just have so many terms in it. And I would just kind of write these at the top of the page somewhere, but these are the three that you need to know. Sine x is the second one, and that one, remember, if you have trouble remembering what powers, that you know that sine and cosine don't have all the powers, they have every other one, just remember that sine is odd. It's an odd function, so therefore it's the one that has all of these odd powers. And so we can write it just has an odd power, so 2n. And remember, you could do plus 1, minus 1. It doesn't really matter because it just depends on whether you're starting with x equals 0 or n equals 0 or n equals 1 or whatever. So just basically I need it to be odd, and whatever the power is, that is 2. And then let me scoot over a little bit. I forgot to put in the multiplier. So we do have to have a multiplier, and it's got to start off positive, so we'll have to have an n plus 1 because the way I've written it, let's see, no, the way I've written it, I'm starting with n equals 1. So if you look at that carefully and try it, if you put n equals 1 in, you'll get x to the first, and then if you put 1 in for that multiplier, you'll get a 1 plus 1, which is 2, so that makes it positive. And then cosine, and another way to remember that one is it's an even function, so it's going to be the one that has all the even powers, and both of them are alternating, so we do need to remember that. And then it's a little easier to write. You're going to have the multiplier, and this time, still 1n plus 1, so we have x to the 2n over 2n factorial. So if n equals 1, then we can't start there. We actually have to start at 0. So actually, if I'm starting at 0, this will have to be n, because I want the first one positive. So if I want to write it this way, which is a little easier way to write it, then I just change that index. So these are the three that we're supposed to already know. And then now today we're going to learn in this next example, which we're skipping example 1. So don't put a big X through the whole thing. We actually need to use some of that blank spot. So you can kind of cross off the example 1, all that big wording, but kind of box off that empty space. And that's what we're going to use next here with this example. So this is the other power series that we're going to do, which is 1 over 1 minus x. So this is the other one that you'll have to memorize. And then if you know those 4, you should be able to do most everything there is on the AP test without having to do a lot of extra work. So we're going to find this power series 3 ways. One by Taylor's rule, which is the way we've been doing it, so that'll be easy and a good review. Then we're going to learn how to recognize that it has something to do with a geometric series, and then we're going to do long division. So you'll have to know that these are other things you can do to get these series. So for part A, to do Taylor's rule, let's actually use that space that's above this problem that was supposed to be for example 1. So just kind of box off that blank area and put an A, and this is going to be using Taylor's rule. So to do Taylor's rule, remember we have the original function, which is 1 over 1 minus x. Well, to make it easier to do the derivatives, I'm going to write it as 1 minus x to the negative 1. and then we find the first derivative, then we find the second derivative, and then we find the third derivative, and so on. And as long as we get the pattern, we can stop at the point we see what's going on here. So here, let's do the derivative. So looking at the way I made it as a power, you would have -1 times 1 minus x to the -2 times the derivative of the inside. Well, the derivative of the inside is just -1. So what that's going to end up doing is getting rid of this, and so I just get 1 minus x to the -2. So now let's do f double prime. So if I do the derivative again, I would have -2, I would have 1 minus x to the -3, and then times the derivative of the inside, which is again -1. Well, I can see the pattern there in that I'm not going to ever end up with anything being negative because all the powers are negative, but then I'm going to multiply by the negative inside. So that'll help a little bit. Let's go to the next derivative. So I would put -3 in front, but in a minute I would be multiplying by -1, so we'll just put 3. And then it's 3 times the 2 that's already there, times 1 minus x to the -4. And let's do one more time, and I think we should see a pretty good pattern here. I'm going to put the -4 in front, but again, that -1 is going to come in and get rid of the negative. So it's 4 times 3 times 2 times 1 minus x to the -5. Well, I can kind of see a pattern there. This first part is just going to be whatever the previous power, or not, but like 1 less than this power. So this is a 5, and this is 4 factorial. So anyway, I can see the pattern there, so that can help me a little bit. All right, so now let's do f of 0. We're doing the Taylor series where the center is 0. So we plug in 0, and we're going to get 1, because we're going to get 1 to the -1, which is still 1. When we do f prime and we plug in 0, we're going to get 1 to the -2, still 1. F double prime of 0, we plug in 1. Well, the 1 to the -3 will be 1, but this time we have this 2 in front. So that's going to give me 2. F triple prime of 0, well, again, I plug the 1 in, the inside's 1, but I'm going to get this, which is 3 times 2, or 3 factorial. If I do the fourth derivative, notice again, same thing, but I'm going to get 4 factorial. So you end up with whatever the power of the derivative is, that's the factorial that you end up with, because of course this could be written as 2 factorial, and so on. So now let's write out the Taylor series that we get using those coefficients. So to write the Taylor series, we're going to say that 1 over 1 minus x equals, we put an equal sign because this is a series. That first coefficient up there, f of 0, is 1, so we get 1 plus. Then we put the next coefficient, which is also 1, times x to the first, so that's x, plus. Now we put the next coefficient, which is 2 factorial. We divide by 2 factorial, x squared, plus. Now we put the next coefficient, which was 3 factorial, over 3 factorial, x cubed. And then you'll have 4 factorial over 4 factorial, x to the 4th, etc. Well, we can see that if we simplify that, that will easily simplify here to 1 plus x squared plus x cubed plus x to the 4th. So very easy to see that this general term is just x to the n. So this is a super easy one. So you can kind of add that to the list of the ones that we need to know. And we will put that, you'll need to make a page in your composition book to put those 4 that you need to know. And that way, before you take the test, you can review them and know what they are. Okay, so we found the series by using Taylor's rule. Now we're going to find it in a couple of other ways, and then when we're done with all that, we'll find the interval of convergence. Actually, we'll find it after the second way. So now down below the problem, we can do part B. And let me extend the page here. So part B says to manipulate a geometric series. So this is what we're trying to do. So we have to look at this and think to ourselves, what in the world does that have to do with a geometric series? Because it's not some number raised to the n or anything. So here's what we're going to notice. If you have a geometric series and you get to the end of the geometric series and you find the sum. Well, how do we find the sum? We take the first term and divide it by 1 minus the ratio. Well, doesn't that look very similar to what I have written over here? Because in fact, couldn't this just be, if I set it equal to this, you can see that A1, which is the first term, is just 1, and R equals X. So in fact, I should be able to write this as a geometric series, n equals something to infinity. We'll figure out whether we start at 0 or 1 in a second. And then it's first term times R to the n. And we can start with n equals, our first term is supposed to be 1, so we'll need n to equal 0 to start that off. So recognizing that this is really just the sum of a geometric series, and what I'm trying to do is write a bunch of plus signs between stuff, that when you add it up, this is the answer. Well, then that's exactly what I just found. There's the sum of a geometric series. Well, this is exactly the series that I just wrote down. But remember, a geometric series doesn't converge always. So we have to figure out, well, when does it converge? Well, that's pretty simple because we have a rule for that. And the rule says it converges when the absolute value of R is less than 1. Well, in this problem, R is X. So this will converge whenever our X, which remember is a different number, but it's a kind of a constant. It's just going to be a number that's plugged in, and then n is what changes. So as long as the X that we choose, the absolute value of it, or X itself, is between -1 and 1, this thing will converge, and it will equal exactly this. So what that tells me is, for that beginning problem, that the interval of convergence would be -1 to 1. But notice how much easier this was. This was super easy to just get an answer really fast instead of going through all that process we just did with Taylor series. We had to find the derivatives, we had to plug stuff in. Here I just simply recognized, hey, this looks just very much like this, or it's, even if it's really close to that, which we'll see in a minute, can I make it look like that? If I can, then it's simply a geometric series, and that's the sum. And there we go. Now I've got the series generated. So that was a much quicker way, and now we just found the interval of convergence without using the ratio test. And guess what? I don't have to test the endpoints, because we know for a geometric series, this is a strict inequality. This is not less than or equal to. If R is 1, this will diverge, and so I'm finished. So really a much quicker way to do that if we notice that. And that's a lot of what math is about. Noticing a pattern, noticing it fits something to make things easier. Notice that we do that. Now we're also going to look at one more thing, which is long division. And the reason we're going to look at this is this will always work. So you can use this for anything that has that basically has a quotient, so to speak. Okay, I can do long division and I can generate my terms also. And so this is also very handy. So basically, we're just going to do long division. So when we do long division, we know that, well, I'm just trying to move that over, but try again. There we go. We know that 1 minus x is what you're dividing into 1. Okay, so we're going to do this division. So we just need to see how many times does 1 go into 1. Well, that would be 1 time. Sorry, the 1 was going in here that we're dividing into 1, and then it goes in 1 time. Now we take 1 times 1 minus x. So let me make sure that makes sense again how I started this, because I kind of messed up when I wrote that. 1 minus x is the divisor, and 1 is what you're dividing. This says 1 divided by 1 minus x. So that's what we write. Now we look, and 1 times what is 1, and that would be 1. Then we multiply 1 times 1 minus x, and we write it down here. Then we draw the line and change the signs because we need to subtract. And when you're subtracting with more than one term, it's a good idea to write it this way. So now we can add 1 minus 1 is 0. That's what we wanted. And then we have just x. So then we think to ourselves, 1 times what is x? Well, that would be x. So then this will be plus x. Then we take x times 1 and we get x. And we take x times minus x and we get minus x squared. Then we're going to draw the line and change the signs. X minus x is 0. That's what we wanted. And then we'll have just x squared left. Now we think to ourselves, 1 times what is x squared? Well, that would be x squared. Then we take x squared times 1 and we get x squared. And then we take x squared times minus x and we get minus x cubed. Then we draw the line, change the signs, and add, and we're going to get x cubed. Well, we keep going. It's not too hard to see that you're just going to keep getting x cubed, then x to the 4th, etc. So we just generated the same exact sequence or series that we just did a second ago right there. So that's another way to generate. Now, the other thing, it says to verify by graphing. Well, part of the reason is, and the reason we need that interval of convergence is, we know for a fact that this polynomial cannot exactly equal this function in all places because this function is undefined when x equals 1. So for sure, at least at that spot, there's no way this is equal. So that means there has to be a place where it converges, and it's close, but it's not the same. So let's actually look on the calculator. Let's actually graph. So let's graph 1 over 1 minus x. Interesting. What is going on here? 1 over 1 minus x. And graph that. And now we're going to graph, and let's go ahead and just graph. I'll graph 1 plus x squared. I'll do several terms because we aren't going to obviously graph it. Don't want to graph all of it, but we can graph, or I mean, we can't graph all of it. We don't want to graph that many, but we'll graph quite a few here so that it's the same for a while. So we'll go up to x to the 4th. Let's even do one more, x to the 5th, and then hit enter. Well, you can see pretty clearly then that this is very close to the same right here. Oh. Very close to the same right in this area. But it is not the same anywhere else. Okay, so clearly, obviously over here, whoops. Obviously, when you get in this area here, I don't know why my pen doesn't want to write on there now, but when you get over in this area, clearly it's not the same. Okay, so, but it is very close to the same between -1 and 1, which is where we just learned it converges. So that's what it means by verify graphically, and it wouldn't hurt you to do that on lots of them. Just so you can see that idea about how close they are. Okay, so let's go to example 3 then. So example 3 says find a power series for 1 over 1 plus x, and then find the interval of convergence, and find the first 4 terms on the general term, okay? So a couple of ways we could do this. We could recognize that 1 over 1 plus x fits that geometric sum formula. If I rewrote this as 1 over 1 minus a minus x, then it fits it exactly where a1, the first term, is 1, and r, in this case, is minus x. So if we use that idea, it's very quick for me to write this series out because I recognize that r is just minus x raised to the n, and the first term is 1. And I start with 0, and there we go. And I've written the general term already. Now, if I want to write the first 4 non-zero terms out, I just have to plug in 0. So if I plug 0 in for n, minus x to the 0 is 1, because anything to the 0 except 0 to the 0 is 1. Then we plug in 1, so we get minus x to the first, so that's minus x. Then we plug in a 2, we're going to get minus x squared, but minus x times minus x, that's what squared means, so minus times minus is plus, and then x squared. Then you put n equals 3, you'll get minus x cubed, and then you can see the pattern there. So that's one way to do it. Super easy. Just look at it and go, oh, look, there we go. It's very simple. Another way to do it is if you had 1 over 1 minus x, we know that one, and this is a super easy one, okay, to remember. So 1 over 1 plus x just means replace every x with minus x. So you would simply put a minus x everywhere you saw x, which would ultimately simplify and end up being there. So there's lots of ways we can do that. We can use a current series and change it, make the substitution. You can recognize it's geometric. Recognizing geometric is pretty simple. And then when you want to find the interval of convergence, well, the same exact interval of convergence will be true here because it will converge when the absolute value of minus x, because that's our r, is less than 1. Well, absolute value of it means when is x, again, between negative 1 and 1. And so same interval of convergence that we had before. All right, so let's go to example 4. So say we want to do x over 1 plus x. Well, we could use the geometric idea again. The difference is the first term here is x instead of 1. Or alternately, we could simply take this one that we already did. So that was 1 minus x plus x squared minus x cubed plus and so on. And all we have to do is multiply it by x. So we just take every single term and multiply it by x. And then so to write the general term here, you would have to have a negative 1 to the something and x to the something. So let's see, if we want to make it x to the n, that means we started with a 1 for n, but we also need to start positive. So this will have to be n plus 1 so that we get an even to start with. And there's your generic series. And so, again, super easy. Now, I could go through the process to do the radius of convergence again, but do you see that it is almost identical to what we've done before? We could do the ratio test, and you're just going to get the same thing. So this is going to have the same interval of convergence, which will be negative 1 to 1 for our interval of convergence. All right, so let's go to example 5. So this one says 1 over 1 minus x squared and find the interval of convergence. So I'm going to use, it's very much like 1 over 1 minus x, which is 1 plus x squared plus x cubed, etc. So all we're going to do is substitute everywhere you see x, we're going to put x squared. That's the difference. So we'll have 1 plus x squared plus x to the 4th plus x to the 6th, and so on, because I'm simply putting x squared in place of x. And so what I've ended up with now are all even powers. So that means I'll have a 2 to the n for my generic term there. And I can just let n start at the right place, which will be at 0, and there we go. So now if we want to find the interval of convergence, well, I'm going to review how to do that with the ratio test. So what we're going to do is take our generic term here is x to the 2n. So we're going to take x to the 2, instead of n, it's n plus 1 over x to the 2n. We take the n plus 1 term divided by the nth term. Well, that's simply the limit of x to the 2n plus 2 over x to the 2n. Simplifying that, you're just going to get x squared. Because 2n plus 2 minus 2n, you subtract your exponents, you'll just get a 2 left. Well, remember that x squared is actually basically a constant in this case. N is the thing that's changing, not x. So that means my limit is actually just x squared. Because if you took the limit of 5, the answer is 5. So x squared is like that. So the interval of convergence then would be, well, this is going to converge anytime that's less than 1. So, and this should have been absolute value to begin with, but there wasn't anything that we were dealing with there that was negative, but let's put our absolute value signs around everything. And then we need to solve this. Well, this is a little different than a regular inequality. We got to solve it looking at it a little different. But we basically, here's x squared. It's a parabola. And we want to know, when is x squared less than 1? That's what it's asking. It says absolute value, but notice that x squared is always non-negative, so the absolute value doesn't actually change anything here. Well, when does this function, when is it less than 1? Well, if this is y equals 1, then we want from here to here. That's when it's less than 1. Well, that's pretty simple. Guess what? It's negative 1 to 1 again. So this is from negative 1 to 1. Now, let's figure out what happens on the endpoints. We haven't done that in a little bit, so let's practice here. So let's find out what happens when x is negative 1. Our generic series was x to the 2n, and we could start at 0 because it started at a 1. So if we look at x to the 2n and we put in x equals negative 1, that's going to give us negative 1 to the 2n. Well, that's going to simply be, if you plug in 0 or 1 or 2 or whatever you plug in, you're going to get negative 1 to an even, which is going to be 1. So you're going to have 1 plus 1 plus 1 plus 1, which is certainly going to diverge, or just do the limit, and this is going to diverge because the limit is not going to be 0. And if you plug in x equals 1, then similarly, you will have 1 to the 2n, which again, if you do the limit, as n goes to infinity, you're going to get a 1, which is not going to converge. That's not equal to 0, so it diverges. So your interval of convergence is still negative 1 to 1. So far we haven't done anything to change that interval of convergence. All right, so let's go to the next problem. Now we want to find a power series for this one. Well, again, take your 1 over 1 minus x, which is 1 plus x squared plus x cubed, etc., and substitute everywhere you see x, we need to put 2x. So we'll have 1 plus 2x instead of x, 2x squared, 2x cubed, and so on. And so we could write that out and simplify that a little bit, or we could leave it. Actually, if we kind of leave it, it's a little bit easier to write the generic term, because this would actually be just 2x to the n, and that would be our general term there. So if we want to find the interval of convergence, let's take the limit as n goes to infinity of 2x to the n plus 1 divided by 2x to the n, because you want the n plus 1 term divided by the nth term. So we take the limit and we subtract your exponents, and you're just going to get a 2x. Again, this is, and we should have done absolute value, this is basically a constant, so we get absolute value of 2x. Now we want to know, when is that less than 1 in order for it to converge. So this time things changed a little bit. Now we've got to actually solve this by dividing by 2. So you're going to get, it's when the absolute value of x is less than a half, or when x is between negative 1/2 and 1/2. Now, we could go through the whole process to plug in the endpoints, but let's see what's going to happen. Let's just do the x equals 1/2. You're going to have 2 times 1/2 to the n. Oh, sorry, 2 times 1/2 is inside to the n. Well, guess what 2 times 1/2 is? That's 1. So we got 1 to the n again. So again, both endpoints are going to end up diverging, and so it is going to converge only for this. All right, so let's do example 7, and then we're almost finished. We will finish the rest of these in class. So this one, we're going to use the idea of that geometric series. So we're going to rewrite this so that it fits that format, because this is a little different. I can't replace x with anything because it is x, and it's the 4 that's the problem. So we need to make that a 1, because in the formula, this is a 1 here. So I'm going to divide that by 4. Well, I can't just do that, so I got to divide everybody by 4. So we divide every single term by 4 in order to make this have a 1 plus something there, because that's the formula. But then the formula is actually minus something, so that'll be minus negative. Well, now this fits. You've got your a1 over 1 minus r. So that means your first term is a fourth, and r is equal to negative x over 4. So if we want to write out our series, our first term is a fourth, and then write negative x over 4 to the n, and equals 0 to infinity, and there we go. So knowing that makes it really easy. If I recognize that it fits that sum formula, then it's super easy for me to write this out. And if I want to find the first 4 non-zero terms, all I have to do is plug in 0, 1, 2, and 3. So when I plug in 0, I get a fourth. When I plug in 1, I will get negative, and I will get a fourth times a fourth, so I'll get negative x over 16. Then when I plug in a 2 for n, that'll make it positive, because an even power will make that go away. And I will have a 16 here if I plug in 2, because I'll have 4 times 4, times the 4, so I'll get x over 64. And then I'll get minus, and that's x squared, x cubed if I go one more time, over 256. And it will continue like that. And that's just numbers. Just plug in for n and simplify it to what you get. Now, what about the radius of convergence here? Well, now what we have to think about is that it converges whenever the absolute value of r is less than 1. Well, this time, the absolute value of r means when is the absolute value of x minus 4 less than 1? So we got to multiply by 4 and ignore the negative. So when is the absolute value of x less than 4? And so that would mean when we go from negative 4 to 4. If you similarly, again, check the ends, if you plug in 4, it will not converge, 4 or negative 4, because you're going to get a 1 times stuff, so it's not going to converge. So it's going to work for that example. Okay, one more example, and then we'll do the rest in class. So here we have 1 over x, and we want to do that. Well, 1 over x does not look like the format that's close to any of those. So we will have to do, I'm going to give you a hint here, but you will normally have to figure out this hint yourself. I can actually make it look like that format if I rewrite it like this. So if I rewrite this term as, or let's not do it that way actually, let's make it 1 plus x minus 1, that'll be easier. So now it actually fits the format of 1 over 1 plus x, but you're replacing x with x minus 1. Now, what that also tells us is it's centered at c equals 1, and that's why I needed the x minus 1 in there. That's why when I wrote it with x plus 1, I realized that wouldn't work. It's supposed to be centered at 1, which means you have to have x minus 1 in the terms. So if I take my 1 over 1 plus x, which is 1 minus x plus x squared minus x cubed, etc., all I'm going to do this one, 1 over x equals 1 over 1 plus x minus 1. So everywhere I see x, I'm going to replace it with x minus 1. And there we go. So pretty simple. So that means our formula for our series is going to be, I have to have a negative 1 to the n or n plus 1. We'll figure that out in a second because it's alternating. And then I'll have x minus 1 raised to the n. So if we start with 0, then that works out, gives me the right signs. And so that's my series. Now, to determine when it converges, this is going to converge when the absolute value of x minus 1 is less than 1. Again, think geometric. This is the geometric sum formula, so it fits geometric. So it will converge when the absolute value of x minus 1 is less than 1. But that means when is x minus 1 between 1 and negative 1. In other words, another way to think about this is I am 1 away from the center, which here happens to be 1. So that's what that means. So that means I'm going to be between 0 and 2. That will give me 1 unit away from 1. And then you have to check the endpoints. Well, again, if you were to check those endpoints, if you plug in 0, you'll have a negative 1 thing there, going to diverge. You plug in a 2, you'll have a 1 there. It's going to diverge because that limit will not be 0. All right, so we will finish the rest of these in class, and then we'll be done with power series.